Okay, so we are now recording, so we can go ahead and get started here. The homework was honestly fairly light, and it really only followed two main themes: cofunctions, and then as soon as you understood cofunctions, you could do the first three problems. And then the second set of problems were basically just verifying your understanding of those special triangles and what falls out of them, being able to have exact measurements for sine, cosine, and tangent, and then obviously the reciprocal functions for specific degree measurements, right? 30, 45, 60, those are the ones that kind of fall out of those special triangles. So does anybody have any questions that fall out from the homework? Anyone in particular that, piqued your interest or stumped you? Number 78. Yes, so 78 was the only one that was a little bit different. 78 was just still verifying your understanding of, what sine meant, basically the relationship of the sides. And with that, you could use it to find values for tan of theta, secant of theta, and then obviously put it together with addition. So we can definitely get to that. I want to try to do one of the earlier questions first, if possible, Keji, just for the sake of 78, although super important, and we'll get to it today. I just want to focus on the special triangle business first. So because that's the newer material. 78 didn't directly wasn't a consequence of the new material. It was really just reaffirming that you understood the last lecture. And by last, I mean previous. So I'll definitely do 78. But is there any questions on like 31, 34, or 36? Or the cofunctions one? 34? Okay. So we'll definitely take a look at 34 real quick, and then we'll go from there. Okay. So if you don't remember the chart that from the lecture, and again, the chart just quickly looks something like, 30, 45, and 60. And then this is what happens if, it was sine of 30, or cosine of 30, and then tangent of 30, right? And of course, once you figure these three out, you can figure out cosecant of theta, secant of theta, and cotangent of theta, because obviously it's just whatever fraction you get for each of these pieces of the chart, it's just the reciprocal of that. Obviously the respective reciprocal, secant going to cosine, cosecant going to sine, so on and so forth. So if you don't remember the chart, totally okay. The first step that you should do, if you ever see, cosine of 60 or sine of 30, any of those, we'll call them special angles, 30, 45, and 60. If you ever see any of those, and you're wondering, what the trigonometric value is at that angle, just build your triangles, your special triangles. So the first thing that we're going to do before we even write down what number 34 is, before we write down the question, let's just build our triangles real quick, just so we have it, and that way we can, derive what we need to derive. So the first triangle, again, 45, 45, 90, right? So this is our isosceles right triangle. Again, we know that from the angle measurements. That's what this is claiming here. It's a 45 degree, another 45 degree, and then a 90 degree, right? So this is going to look something like, not like that. This is going to look something like, yeah, it's a bit better. Why not? With the idea here that, again, the two legs will be equal to each other, right? So I can draw like little hash marks right here, and that is just a sign that they're equivalent. We obviously put the right angle opposite the hypotenuse. Okay, we're in business. So what are the proportional measurements for 45, 45, 90? What should I have for my leg, my other leg, obviously, and then my hypotenuse? Anybody remember from the lecture? Yes. Grace, and also somebody raised their hand. Keji, either one of you, or both of you.
A.
Yeah, so A is for my leg, sure. What's the other leg then?
A.
It's also A. Great, yeah. Okay, and then finally, what's the relationship between the leg and the hypotenuse? What should the hypotenuse be?
A2. A2 under the radical.
Yeah, A times square root of 2. Whatever the value is of the leg, you get the hypotenuse for free. That is just the length of the leg times square root of 2. And that's how it works with a 45, 45, 90 triangle. So perfect, great. And obviously, if this is a 45, 45, 90 triangle, we can just draw a little 45 degrees here, right? And that's going to help us in establishing what these trigonometric values are at that specific angle, at 45 degrees. Okay, perfect. And now let's go ahead and draw our second special triangle. So 30, 60, 90. Great. Let's go ahead and pull this up. So to do this, my triangles look less and less like triangles every time I draw them. So the top one here, of course, the smallest angle is going to be the 30-degree angle. It's going to be the 60, and the 90 degrees indicated by the box, right? The right angle. And okay, so remember, guys, this is your last week to earn participation credit. Anybody else want to try to help me out? What are the measurements here for the other piece? Yeah, Shelby, what's the first leg, the one opposite of 30 degrees?
A.
Great. What is the second leg? So over here.
A radical 3.
Perfect. A times radical 3. And then finally, what's my hypotenuse?
2A.
2 times A. Great. So what this is telling you is that as long as you know one of the other sides in a 30, 60, 90 triangle, you only need to know one side. You can derive the other ones, right? If I gave you the hypotenuse, for example, then you know for free that the smallest leg is half of the hypotenuse, right? If the hypotenuse is 2 times A, so half of that is just A. So you can derive the other pieces of this just given the fact that you know it's a 30, 60, 90 triangle and one side tells you the other two. But great, okay, so we have this set up. Let's go ahead and now write down the question here. So the question we have is simplifying cosine of 60. So we have cosine of 60 degrees times cosine of 45 degrees minus sine of 60 times sine of 45. So sine of 60 times sine of 45. Okay, we somehow have to simplify this. So right now, as it currently stands, there's not a whole lot that we can do until we look at the relationships that we have. We have to basically substitute in for every single one of these trigonometric values. We have to substitute in a fraction. When we do that, then it's just a matter of multiplying and subtracting fractions, and then we're basically done. So let's start off with cosine of 60. So over here, actually, it would make more sense to do it over here. So over here, let's start figuring out cosine of 60. Okay, so Ashley, help me out. What is just the relationship for cosine? What should, the two pieces that I'm looking at whenever I'm talking about cosine?
You're looking at
So basically just, two sides of the triangle. One of them is going to be on the numerator of the fraction. One of them is going to be on the denominator of the fraction. You don't even have to tell me the specific numbers or values. I'm just looking for, the words that define them. If you know the values, though, that's great.
sorry,
No worries.
it would be the adjacent and hypotenuse.
Yeah, so it's for cosine, whenever you're dealing with cosine, perfect. It's always going to be adjacent, which, just to clear things up so you don't think I'm talking about side A here, adjacent over hypotenuse, right? That's always going to be the case whenever you're dealing with cosine. And then it's just a matter of angle and figuring out what's the adjacent side, what's the hypotenuse. Well, the hypotenuse never changes, so you always know your hypotenuse. So that tells us, okay, well, my hypotenuse never changes. I know it's going to be 2a, right? No matter what 30, 60, 90 triangle, it's always going to be 2 times whatever the length of the smallest side is. And then my adjacent angle, so again, keep in mind, we're talking about 60 degrees. So my adjacent side here to the 60 degrees is going to be just the little lonely smallest leg here, just A, right? So when we draw this, or when we put this into a fraction, again, notice, as we talked about in the lecture a little bit, that it doesn't necessarily matter what the length of the side is, as long as things remain proportional, right? Because the A's are going to cancel out, and you're always going to be left with just 1 over 2, right? When the A's cancel out, you get a 1 on top, the 2 remains, so you just get 1/2. So great, we already figured out what this trig function is, cosine of 60. Let's, before we leave this triangle, because I see that we also have a sine of 60, let's figure that one out as well, and then we'll go from there. Okay, so sine of 60 degrees, we're going to do the same thing. Again, we're just going to set up this relationship, and then with that relationship, it'll tell us the fraction, right? So can I get a volunteer? Just help me out. What's the relationship? Same thing that we figured out for cosine. What's the fraction going to be for just sine? Yeah, Keji.
Radical 3 over 2.
Oh, you're already jumping the gun, getting straight to the action. Okay, I was just looking for.
Oh, sorry. Then it would be over H.
Yeah, opposite over H, right? Yeah, and Aline's got it as well. So opposite over hypotenuse. That's always what it's going to be whenever you're dealing with sine, right? So we look and we see, all right, well, what's my opposite side of 60 degrees? Again, keep in mind, in this case, we're looking at the angle of 60 degrees because that's what it's asking of us. So looking at 60, we look and we see the side that's opposite, and we say, okay, that's A times square root of 3. So great, we know the opposite side. So we have A square root of 3 up top. And remember, again, the hypotenuse never changes. Just like we saw, hypotenuse is still 2 times A, so we can throw that in the bottom here. And once again, we see the sides don't actually matter because we have A on top and A on bottom, so those are going to cancel out. And just like Keji said, square root of 3 over 2. Great, so now we have another piece of the puzzle. So all there's left to do is figure out what cosine of 45 is and sine of 45 is, and then we're good to go, right? But for that, we need to hop back over to the 45, 45, 90 triangle, because this is the one where 45 degrees exists. So this is the one where we can establish the trig functions for 45. Over to the angle here. The cosine, let me make more room for myself here. Cosine 45 degrees. Okay, as we already established from over here, we already talked about how cosine, regardless of the angle, is just going to be the relationship of adjacent over hypotenuse, right? So we know, again, it's adjacent over hypotenuse. So what is here? Who can help me out? One more other than Keji. Sure, Shelby.
Radical 2 over 2.
Radical 2 over 2. Okay, so if you want to explain how you're getting that for me.
Because, well, I looked at the chart from the lesson.
That always works.
Is that a good answer?
That's a fine answer, sure. So the way that we can derive it, though, in case you don't have the lecture in front of you on the test, for example, is notice, again, we're talking about 45 degrees, right? So 45 degrees, we're looking at the side that is adjacent to 45 degrees. So in this case, the side that's adjacent to it is A. Now, notice that it actually doesn't really matter if we're talking about adjacent or opposite, because if we were talking about opposite, we'd also get A. So sine of 45 degrees should come out to be similar, and we're probably going to see that in a second here. But in any event, adjacent to 45 degrees, we get side A. So that means we have A over, and our hypotenuse is A radical 2, right? So we have A radical 2. The A's are going to cancel out, so we're left with 1 over square root of 2. And all we have left to do is just rationalize this piece. So rationalizing this, hopefully you all remember how to rationalize. If you don't, start practicing now. So to rationalize, we have the square root of 2 in the bottom. So we know we need to multiply by a square root of 2, but that means, if we're multiplying the bottom, we also have to multiply the top to not change the value. And we end up with square root of 2 over 2, exactly like Shelby said, or exactly like I said from the lecture, however you want to look at it. So in any event, we get square root of 2 over 2 for cosine of 45. So all there's left to do, we solve for cosine of 60, cosine of 45, and sine of 60. So we just need to figure out what sine of 45 is, and we're good to go. Why do we rationalize? You don't actually have to rationalize immediately. If you don't want to rationalize until the end, that's okay. It's just that in general, when we're dealing with trig values, we tend to rationalize the fractions. Number one, because it looks cleaner, and number two, because it helps you gain a certain sense of what is, the actual values are. If I told you that you had 2 being divided by square root of 2, that, if I told you you had 1 being divided by square root of 2, you might not actually have any bearing of what that means, right? But if I told you you had square root of 2 being divided by 2, well, square root of 2, we can figure out is basically a little bit more than 1. The way we can figure that out is, well, square root of 1 is equal to 1. Square root of 4 is equal to 2. And you know that square root of 2 is a lot closer to square root of 1 than it is to square root of 4. So square root of 2 should be closer to 1 than it is to 2. But in any event, so you get something that's a little bit larger than 1. You're dividing it by 2. So you can imagine that just using a logic, if you really wanted to get a value for this fraction here, you could approximate this to be somewhere around like 0.6, for example. So it just gives you a better sense of what's going on, and that's in general why we rationalize things. Also, it helps with common denominators in more complex problems. But anyway, good question.
Wait, now I just have one more question about
Sure.
that. So like the numerators, they just equal 2. Oh, right, because it would be 4. Okay, thanks.
Yep. So we get square root of 2 times square root of 2, which gives you square root of 4, and square root of 4 simplifies down to give you 2. Yep. Any other questions on the rationalizing thing before we move forward? Okay, good question. All right, so let's go ahead and now just establish the sine of 45 degrees. That's the only last piece we have to do. So sine of 45 degrees. Sine, as we just discussed, is supposed to be opposite over hypotenuse, right? So I'll just do this one. So opposite over hypotenuse. And just like I was saying before, in a 45-90, since opposite and adjacent, regardless of the angle that you're talking about, because they're both 45 degrees, come out to be the same thing, we know that we should actually just get the same thing, right? So it should be a over a radical 2, and I'm just going to simply skip the simplifying piece here, so we should just end up with square root of 2 over 2 for sine of 45 as well. And also, this should make a decent amount of sense, because if you guys remember cofunctions, like we were talking about in the last lecture and also the beginning of this homework, cofunction of sine of 45 degrees, just going off on a quick tangent, if, I told you find theta in this case for cosine, so find the angle that makes, this equation true. Well, remember that to find that cofunction wise, you're just subtracting this original angle from 90 degrees, right? So 90 minus 45, and you end up with cosine of 45 regardless. So sine of 45, cosine of 45 are equal, and that's what I was getting at in the lecture before, is that these, the cofunction pairs become, the degrees of them are equivalent at 45 degrees. So we can see that showing up in this case as well. Okay, so great. We actually have all of the sides figured out, or all the angles figured out, rather. So we just need to plug in these fractions and then simplify. And once it's simplified, we're done, right? So cosine of 60, what did we figure that out to be? We got that to be 1/2, right? So we have 1/2 times cosine of 45, we figured that out to be square root of 2 over 2, minus sine of 60, which was square root of 3 over 2, times sine of 45, which also, again, is square root of 2 over 2. Okay, so at this point, we see that we actually already have a common denominator, right? Everything is in terms of 2 on the bottom, so that's going to help us out with the subtraction. So let's just do the multiplication just to simplify stuff, and then we'll get to the subtraction. So the multiplications, when you multiply fractions, again, you're just multiplying across top and bottom. So you have 1 times square root of 2 on top, which gives you square root of 2, and you have 2 times 2 on the bottom, which gives you 4. Then for the other piece, square root of 3 times square root of 2. So if you have square root of 3 times square root of 2, remember that when you're multiplying numbers who have the same exponent or who have the same root, you can combine them into one single piece, right? So square root of 3 times square root of 2 is really just the same thing as square root of 3 times 2. And we know that 3 times 2 is, of course, just 6. So we would end up with square root of 6 over here. And of course, 2 times 2 on the bottom still leaves us with 4. And now we can do this final subtraction piece where you just get square root of 2 minus square root of 6 over 4. And there's really no more simplifying this. There's really nothing else that you can do. If you wanted to do the subtraction up top, be my guest, but this is as simplified as you can get it as a fraction. A lot of you guys have a habit of, still wanting to convert fractions to decimals. Just don't. Just leave it as a fraction. There's very few times where a decimal is actually going to be the thing that you're looking for, mainly because this here is the exact answer. This is as exact as you can get it. This is as simplified as you can get it. As soon as you convert it to a decimal, especially if it's an irrational number, that number goes on forever. So the best that you could do is you can draw this little approximation symbol and say, okay, well, it's about, whatever number comes out of your calculator, right? Which we don't necessarily care about. Yes, Keji.
I had a question about one of the other homeworks, but I'll just wait till you're done.
Okay, sounds good. Okay, so again, just leave it as a fraction. This is, again, as simplified as we can get it. The question specifically says simplify this, so just simplify it. Just leave it as that. You don't need to give me a decimal, specifically on like a test or a quiz. Just leave it like this. Okay, anybody have any questions now that we've kind of ran through this one together? Again, the idea is regardless what these angles are, what these, the trig functions are, you can just build your special triangles as we saw, and you can derive any of the 6 trig functions at those specific angles. So 30, 45, 60, you can always figure it out, like secant of 30, for example. And to do that, you would just look at this triangle over here. So any questions? Okay, so we'll go ahead and move on here. Numbers 31 and 36 are very similar. I will say there is a very, very clever trick that you can do with number 31. I'm not going to do the entire thing because I know I still need to go back to number 78. But just to show you the thing that you can do. So if you didn't want to do all of that work of figuring out, so for number 31, it says, let me just write it down first. We have sine of 60 times cosine of 30 plus cosine of 60 and times sine of 30. Okay, so if you didn't want to figure out 1, 2, 3, 4 trig functions, you can actually use cofunctions to simplify this down. And the reason that you could use cofunctions here is because you actually remember the pairs, right? That tangent is a cofunction to cotangent. Secant is a cofunction to cosecant, and sine and cosine are cofunctions of each other, right? So you can just actually change this to be in either all terms of cosine and, cofunction out those sines to cosines, or you can change the cosines to be in terms of sine. So just to get it in terms of all of sine, again, just to show you that it's possible, that means I want to use my cofunction identities to replace cosine of 30 and cosine of 60, right? So that's basically saying, okay, if I have cosine of 30 and I want to convert it to sine of something, sine of some degree here, well, to do that, the idea is that we just want to use cofunction property that we talked about before. And so this is basically the same thing as sine of 90 minus 30 gives me sine of 60, right? It's just the complementary angle to whatever this piece is. If you guys remember supplementary and complementary, complementary means it adds up to 90. That's all cofunction identities are, is that it's just 2 complementary angles and the trig function switches from, whatever it is from the first part of the pair to the second trig function of that pair. So we know that cosine of 30 is sine of 60, and then translating the cosine of 60, I'm not going to spend too much time on this. Again, same exact procedure. We see that cosine of 60 ends up just being sine of 30. So that means we can actually rewrite this statement that we started with up top, and we can rewrite it in terms of only sine. So when we do that, we get sine of 60 times, another sine of 60, right? That's exactly what we just figured out cosine of 30 to be, a second sine of 60 there. So we have sine of 60 times sine of 60 plus sine of 30 times sine of, again, another 30 here. So sine of 30 times sine of 30. And now, instead of having to figure out 4 different trig functions, so 1, 2, 3, 4, you actually only need to figure out 2. You just needed to figure out sine of 60 and sine of 30, because this is essentially over here, this is essentially sine of 60 squared, right? And then for this one over here, this is essentially just sine of 30 squared. So once you figure out sine of 60 and sine of 30, this becomes fairly trivial. You just square them, whatever the fractions are, and then add them together. Okay, so again, I'm not going to go through that entire procedure of showing the triangles and figuring out what it is, but we can see that we can actually simplify certain problems just by using cofunctions. Yeah, Keji.
Is there a different way to solve that?
Yeah.
Because I realized that sine of 60 and cos of 30 were the same. So instead of writing down what you just wrote, would we multiply radical 3 over 2 twice? And then,
Well, that's exactly what you would get at. Figure out you
it's kind of confusing because you wrote so much. Okay.
Well, yeah, but this was to prove it, right? So if you realize that it's the same, that's great, and you can just plug it in because you're realizing it from your chart, or however you figured it out, that the two pieces were equivalent: sine of 60, cosine of 30, and then vice versa, cosine of 60 and sine of 30 should both be equivalent pairs, right? They should be equivalent to each other. So when you end up saying, okay, yeah, cool, these are in fact the same thing. Well, it's just the same. You're just taking that one fraction that you get and then squaring it. So the reason that I is just showing that, rigorously, that this is where it's coming from. That, it's not just some crazy magical coincidence that, you're coming up with the same fraction twice. But in any event, again, you can just derive it from the special triangles the same way that we did number 34 together. So whatever makes more sense to you, be my guest. I'm just showing you that there are alternative methods, and trigonometry is very, very weird like that. Okay, so with all that being said, I'm going to jump to 78 unless there's no objections here. 78, again, is a little bit of a doozy, but once you see it, it'll make far more sense. So we'll start going through it together. So we are given a right triangle. So let's start by drawing a right triangle. It doesn't actually specify if it's a 45, 45, 90 or a 30, 60, 90. So you just draw a right triangle and just say, okay, this is my triangle. Sure. I'm just going to pick one of the angles at random here. That's not the 90-degree one, to be theta. So right over here, I'm going to say this is theta. It doesn't actually matter which angle you pick to be theta, as long as you draw this correctly, as long as, your sides, resemble what I'm drawing. If you picked this angle to be theta, then you're just going to have flipped opposites and adjacent sides. But again, it shouldn't make a difference. Okay, so with this giving to us, again, we're given that it's a right triangle. We're also given the fact that sine of theta, so sine of theta is equal to m squared minus n squared all over m squared plus n squared. And what we have to do is we have to find the value. So we're looking for the value of tangent of theta plus secant of theta. So we're looking for this. This is our unknown. Okay, so the way that we should proceed here is by filling in as much information on the triangle as we can possibly manage, because notice how we have to figure out tangent and we have to figure out secant, right? So to do that, we should figure out the sides of the triangle. So when we can just directly substitute in those sides for tangent and secant with their appropriate, relationships of the sides. Sorry, I had a sneeze there. So let's go ahead and try to fill this in as best as we can. First off, what's the information that we're given? What does this tell us? The sine of theta being, a fraction, or just whatever it comes out to be, this number. What's the relationship again for sine? So I should have some
And-
side up here and some side down here, right?
Is it adjacent over hypotenuse?
So that's for cosine, which,
Oh.
good try though. I mean, again, you had a 50-50 shot, right? So good try. For sine, it's opposite over hypotenuse, right? So opposite over hypotenuse, just like Deborah said. Yeah, perfect. So what we're going to do is we're going to take our theta, we look and we say, okay, we have theta right over here, right? So the side that is opposite to it, well, that's going to be right here. And of course, hypotenuse is always the piece that's opposite the right angle, right? And again, just hypothetically saying one more time, it's not incorrect if you put your theta up here. Just understand then if you put your theta up there, your opposite side would now be the lower leg of the triangle, okay? But totally okay to do that. Regardless how you draw it, should come out to be the same thing. So opposite sine, opposite of the, or side, opposite of the angle theta. Well, again, that's going to correlate to the numerator of my fraction, right? So that's going to be this m squared minus n squared business. So we know that right over here, we have m squared minus n squared. And then for our hypotenuse, well, that should be m squared plus n squared, right? That's the denominator of our fraction. Again, remember how this correlates, right? We have whatever's up top is our opposite side, whatever's on bottom is the hypotenuse, right? Okay, so we still have this missing side down here, which I'm just going to call x. Well, if we're not told if it's a 30, 60, 90 triangle, and we're not told if it's a 45, 45, 90 triangle, we can't use any of our clever tricks that we just learned about, you know, with the proportionality of the sides. But what we can do is we can always rely on the Pythagorean theorem, right? Pythagorean theorem says if you have sides of a right triangle, you can always figure out the third one. So let's set up Pythagorean theorem. One more time, that's a squared plus b squared is equal to c squared, right? C, as we have already come to know and love, or hopefully I've beat it into you guys, this is always your hypotenuse, right? That letter, C, is always going to be the longest leg, the piece that's opposite the right angle. So when we fill that part in, we know that we're going to have the entire quantity of m squared plus n squared squared, right? That's, this square is corresponding to that piece right there. Okay, so we have that there. We'll worry about simplifying that shortly, but for right now, we can just leave it. Let's go ahead and fill in one of the other legs. And now notice that the other missing leg is what we're solving for, right? So over here, let's say A is the entire quantity of m squared minus n squared, quantity also squared, plus our missing side, which I'll just call again x, so x squared. Okay, so this might look very daunting as far as how we're supposed to solve for this, but luckily for us, going way, way, way back to the beginning of the semester, we have these certain properties as far as factoring is concerned, or as far as expanding, right? So the properties, if you guys remember, if you have any two terms being added together and it's being squared, you should always end up with a squared plus 2ab plus b squared. Who remembers the other one? A minus b squared. What should I get for this? It's going to look very similar. There's going to be one slight change. Somebody other than Keji to help us out. Sorry, Keji, you've answered so much today. I want to give other people a chance. Oh, come on, guys. I know you know this. Don't be shy. You can always do foiling, right? What's a minus b squared?
I
Sorry,
think,
Sophia, go ahead.
yeah, so it's gonna be a squared minus b squared.
Okay, so there is going to be a b squared.
A squared minus, okay, I'm sorry, a squared minus b.
Okay, so there's going to be a b, sure.
Yeah, plus b.
Minus b plus b?
Mm-hmm.
Okay. We're getting closer to what we need to have.
I'm sorry, I'm gonna do it on paper.
Okay, sure. All right, so Deborah has beat you to the punch, but that's fine. So again,
sorry.
No, that's totally fine. So just to show the process here, if we wanted to foil things.
Sorry.
No, you're okay. No worries. So a minus b times a minus b, right? Again, if you don't remember the blueprint, totally fine. FOIL it out, right? What should we always get when we FOIL? So FOIL means first, outside, inside, last, right? So to do first, that's the a times the a, we get a squared. To do the outside, that's a times the negative b, so underlining in red, so that's outside, right? A times the minus b, so that should just give us a minus ab. Then we have to do the inside, which notice now that's going to still be a minus b times positive a, so that should give us another minus ab. And that, explains where you were coming from, Sophia, when you said, the b twice. That's because that's what's actually going on, right? We see that we do have b coming up twice here. And then last but not least, we have last, which is negative b times negative b, and that should just give us b squared, right? The negatives drop out when you multiply two negatives together, and now we can condense this to just be a squared minus 2ab plus b squared, right? So the missing piece up here was the minus 2ab. So I'm just going to go ahead and erase the work that we did for the foiling. And now we see, yeah, sure, we have these two blueprints that always, no matter what the values are, no matter what the numbers are, this is always going to be the case. This will always help you expand, right? And also take very special notice that the minus correlates to the minus of the 2ab. The plus correlates to the plus of the 2ab. A squared and b squared are always going to be positive, regardless of what you end up doing. Okay, so we go back over here, and let's try to do this one first. So m squared is going to correlate to just be my a. So notice I actually do have a situation where it's a minus b, right? M squared is my a, n squared is my b, right? So when I expand this, well, let's just look at our blueprint. We should start with an a squared, right? So in this case, should be m squared squared, right? That's where this is coming from. So m squared squared, we can always use our property of exponents here. Remember, when you have a base raised to an exponent and that's raised to a second exponent, you're just multiplying the exponents together, right? So m squared squared is really just the same thing as m to the fourth. Okay, great. So first part of that is done. Now we have the piece where it's minus 2 times a times b, right? So we put a minus, the 2 is always going to be there. So minus 2 times a times b. Well, we already established m squared is my a and n squared is my b, right? So it's just minus 2 times m squared times n squared. And the last thing that we have to do is just do the plus b squared part, right? So when we do the n squared squared, we actually end up getting the same situation where we have, a number raised to an exponent, raised to another exponent. So we can simplify that to just be n to the fourth. And then, of course, this x squared was still hanging around here because, it was just, tagging along for the ride. Does everybody understand how I got these numbers here just before I move forward? I just want to make sure that we're all good. Again,
Can you just go over that again, please?
Going over one more time? Sure.
Yeah.
Okay.
Thank
So
you.
yeah, absolutely. So there's two ways that you can approach it. Again, the first way is you can just use this blueprint that we just talked about right here, right? Where you're just assigning values for A and B, and then it just kind of falls out. The second way, which might be the more intuitive way, is, okay, well, I have this number, whatever this number is, being squared, right? So if we rewrote this, this is the same thing as, and I'm just going to do my rough work on the side over here. It's the same thing as m squared minus n squared, and then again times m squared minus n squared, right? So what I could do here is I could just FOIL. I'm now realizing my m's and n's are blurring together, so give me 1 second to clean that up, because I don't want any confusion here, or at least any more than there's going to be normally. So great. We can now go ahead and just go ahead and FOIL, right? So again, FOIL means first, outside, inside, last. So FOILing, first is the m squareds. So I have m squared times m squared. Remember, when you have, and I'm just going to do this on the side one more time. We're doing more and more side work. When we have m squared times m squared, again, remember when your base is the same and you're multiplying, all you're doing is you're just adding your exponents, right? So you keep the base the same, it's still going to be m, and then you add the exponents together. 2 and 2 add together to give me 4. So when I do first part of FOIL, we get m to the fourth, just like we got earlier. Okay, now we have to do outside. So outside is going to be m squared times the minus n squared. So when we do that, there's really not any simplification that we can do. We just have minus m squared n squared, right? One of them was negative, one of them was positive, so you just throw the minus sign in there because, of course, it's going to be a negative number. Everybody with me so far? Just want to make sure I haven't lost anybody just by starting FOIL. Okay, taking silence as we're golden. We're going to keep moving then. So we have m to the fourth minus m squared times n squared. And now, so that was outside, we have to do inside. So inside means minus n squared times the m squared, the other one, right? And notice we just get the same value again. So we just get minus m squared n squared again. And the last thing that we have to do, so the last part of FOIL, is the last pieces of each of the binomials, right? So we have negative n squared times negative n squared. Negatives drop out because you have two negatives being multiplied against each other. So you just have n squared times n squared. And remember, just like we established over here, as long as your base is the same, you're just adding the exponents together. So we should end up just getting a positive n to the fourth. So what we just have to do is condense the middle pieces because we see that we have the same thing twice, right? We have a negative m squared n squared, and again, minus m squared n squared. So when we condense this, m to the fourth minus 2 m squared n squared plus n to the fourth. Are we good on that now? Does that make more sense? Again, sometimes following the blueprint can be a little bit tricky if you don't see the immediate, substitutions that you're making. But if you just follow foiling or expanding, you should end up at the same value regardless. Okay, again, going to take it as we're good to go. So let's go ahead and just keep on chugging. We have to do the opposite side here. And just with the interest of time, I'm just going to do this. Again, feel free to FOIL it out, or feel free to try to follow the blueprint of a plus b quantity squared. Either way, you should end up with m to the fourth plus 2m squared times n squared plus n to the fourth. Again, notice that when we ended up expanding this, the only difference between the two pieces is there's a minus here that correlates to the minus from above, and there's a plus here that correlates to the plus from above. Either way, you're gonna they should resemble each other very, very closely, just with that slight difference. Okay, so keep in mind when we started all of this mess, we were doing it in an effort to find x, right? So we still are trying to do that. So we still have this x squared that we want to solve for. Well, when we're solving for a variable, much like we saw on number 4 of the project packet, or for other situations that we've used Pythagorean theorem, when you're solving for a specific variable, that means move the other garbage to the other side, right? You're just solving for one particular value. So that means all of this garbage over here, I'm just going to subtract or add in, the case of the negative 2m squared n squared. So I'm going to subtract the m to the fourth on both sides. And I don't normally do this, but I'm just going to keep track of exactly what I'm doing. So subtract the m to the fourth on both sides. I'm going to add the 2m squared n squared and subtract off the n to the fourth, right? And so again, same idea, whatever I do to one side, I'm also doing to the other. Okay, so when we do this, and I have to make some room for myself, one moment. There we go. So when we do this on the left-hand side, we see that everything cancels out, and that was the entire idea, right? We're subtracting m to the fourth on both sides, so that way this number right here just drops out, right? So the m to the fourth is going to go away. We're adding 2m squared n squared, so that way this piece drops out. And we're subtracting n to the fourth so that that piece drops out. So all we're left with is just x squared. Great, we have x squared all by itself. Now we go over to the right-hand side and see the effects of what we've done, right? So we subtracted m to the fourth. Well, we had one m to the fourth already, right? So that's going to go away. We're adding 2m squared n squared to an already existing 2m squared n squared. So now if you have 2 of something and you're adding another 2 of that same something, you should end up with 4 of that something, right? So 4m squared times n squared. And lastly, this piece cancels out as well, right? So that n to the 4th minus n to the 4th, that just goes away. Okay, well, this simplified greatly, right? We don't have anything to the 4th power. Things are looking a lot more clean now. Our highest power is a square, and luckily for us, we know what's coming, right? We're trying to solve for x, so we're just going to take the square root of both sides. So taking the square root of both sides, I have x down here, and now we just go through one by one and see if we can, in fact, take the square root of it. If we can, great. Take the square root of it, see what it simplifies to. If you can't take the square root of it, just keep it underneath the square root, and, that's it. There's nothing else that you can do. In this case, though, everything should simplify, right? What's the square root of 4? Should just give us 2. Square root of m squared is just m, and square root of n squared is just n. So, in fact, we have just simplified this, and now we've solved for x. X is just 2 times m times n. So we go back to our triangle, and we say, great, this is 2mn. Okay, we have done a tremendous amount of work to find this one side. Why does that side help us so much? Well, now it allows us to figure out what tan of theta and secant of theta are. So we one more time do some rough work, and we're going to put it over here so we can keep the triangle in mind. Tangent of theta. All right, what is the relationship for tangent? It's a relationship of 2 sides, right? Separated by a division. So what are my sides here? Anybody can help me out. Opposite over adjacent. Great. Perfect. So tangent of theta is opposite over adjacent. And now somebody who's not Keji or Deborah, help me out for secant. What should secant of theta be? It's still a relationship. Yes, Zenaida, help me out. What's this going to be?
Adjacent over opposite?
Adjacent over opposite. So that would be
hypotenuse.
that piece flipped, right? Yeah, hypotenuse. So adjacent over hypotenuse. Okay. So before we proceed, does this look right? Well, ask yourself, what's cosine? What's cosine of theta here? Don't give me a number, just tell me the relationship. So just going to write this over here. What is cosine of theta? We have a relationship for sine a couple times today.
Is hypotenuse over opposite.
Ooh. Remember, for cosine and sine, it's always going to be hypotenuse in the bottom, right? So regardless if you're talking about cosine or sine, hypotenuse always goes in the bottom. And for cosine in particular, it's adjacent over hypotenuse. Now remember, secant is going to be the reciprocal of that, right? And a reciprocal of a fraction is essentially just taking that fraction and flipping it. So the reciprocal of cosine, instead of it being adjacent over hypotenuse, we actually see that secant of theta should just be hypotenuse over adjacent. Remember, secant is the trig function that's the reciprocal of cosine. So as long as you remember cosine, you can figure out the relationship of secant. Okay, so we now have our relationships. Now we just need to figure out what those values actually are. So tangent of theta. Okay, we have to do opposite over adjacent, right? So opposite over adjacent, what should that come out to be? Well, opposite of theta, as we drew this, should be m squared minus n squared, right? So this is m squared minus n squared all over the adjacent leg to the theta, which should be the 2mn. So over 2 times m times n. Okay, I'm going to get rid of the relationship here just for the interest of space. But again, we're looking at hypotenuse over adjacent. So hypotenuse over adjacent, we know the hypotenuse that was given to us. So that's the m squared plus n squared. And this is all over the adjacent piece, which we just solved for. So 2 times m times n. And I should have just enough time to finish this up, guys. So just stick with me here. So now we have the 2 fractions. Let's go ahead and plug them in. And again, I'm just going to make space for myself just so not everything is so cluttered. Okay, so one more time. Again, tangent of theta, and it's plus secant of theta. Well, we just figured out that tangent of theta is the m squared minus n squared over 2mn. Then we are adding this to the secant of theta, which we also figured out to be m squared plus n squared, still over the same divisor. So m squared plus n squared, still over the same denominator, right? Over the adjacent side, which is still 2mn. And great, well, we have fractions, we're adding fractions, so we would need a common denominator, but we have a common denominator, 2mn, so we can just go ahead and add the numerators together, right? So when we add numerators together, well, when we add fractions together in general, that just means you're keeping your denominators the same, so 2mn, and you're just adding up the top and the bottom, right? So add the top and the bottom, let's see what we end up getting here. So we have the m squared, and we have plus another m squared, right? I'm just grouping these things together. And over here, we have, oops, sorry. Didn't mean to put equal sign there. We have squared plus that n squared, right? So I'm just putting the matching terms closely together. You didn't have to put it in that order. Again, addition, we discussed the properties, associative, commutative, right? So we can throw them in whatever order that we want. But in any event, we see that certain things start canceling out, right? So when we cancel stuff out, n squareds and the n squareds go away, the negative n squared plus n squared. So what do we actually end up having? Well, this fraction comes out to be m squared plus m squared up top. So that's 2 of m squareds over 2 times m times n. We see the 2's are going to cancel out, so 2 over 2 goes away. We're left with m squared over m times n. And wait, we have an m squared up top. We have a division of m in the bottom. So one of these m's up top is going to go away. And that means we are finally left with our answer of m over n. So it might seem like we did a tremendous amount of effort, but when you really look at the steps that we did here, it's not so bad. I know it seems bad, but it's not so bad. We started with, just given the fact that this is a right triangle and sine of theta is this fraction over here, we derived 2 of the sides of the right triangle for free. We then used the Pythagorean theorem to find the missing side here, which in this case was 2mn. And now that you know all 3 sides of the triangle, well, you can just use the the relationships that we know about tangent of theta being opposite over adjacent and secant of theta being hypotenuse over to figure out what those fractions are supposed to be. You add them together, and it's just a matter of a little bit of simplification and crossing out, and we just end up with m over n. It's like 3 steps, even if those steps seem a little bit convoluted. Any questions on this? I know I'm just ran over my time here, so I don't want to keep anybody if you guys have to go to another class, but hopefully this all makes sense to you. Alrighty, guys, so I'm going to call it. I'm going to stop the recording here. I will be posting the review questions tonight, so try them over the course of tonight so that on Friday, you can come in, we'll start discussing those questions together. I believe on Friday, I'm also planning on just going over project packet number 6, mainly because we didn't have time to do it. I said I was going to post the solution to it, but then I realized that number 6 is like the only one where there's like a whole bunch of different ways to do it. So, you know, yeah. Is there a quiz on Friday? Do you guys want a quiz on Friday? I wasn't planning a quiz on Friday, but if that would make you guys happy, I have no problem. No? You sure? I have no problem doing it.
It's gonna be
okay. So people don't want the quiz. My mistake. See, here I thought you guys were asking about it because you wanted one. Okay. All right. Now I understand. No quiz. Okay. Yeah, no, there's no quiz on Friday, guys. We're just going to be doing strictly review. All your quizzes are done at this point. So just review. Make sure you try the review questions, and, you know, Friday we'll discuss it. What date is the final? The final is Wednesday the 9th at 11 a.m. So you basically show up to class like you normally would on Wednesday, but it's not going to be class. It's going to be your final. I'll remind you once more today and then once more again on next Monday, but should be Wednesday the 9th from 11 to 1:30. All right, guys, I'm again going to end the recording because I didn't do that yet. Let me just do that real quick. What? Did the recording stop before? Oh, no, it didn't. I lied. No, we're good.